Anyway, yeah. Thank you so much for joining this NLP reading group. So we are excited to present our latest work from the nlPUG group at UTS, which is preference-driven LLM alignment using representation editing. So this has been accepted in the ACL main track as a short paper in 2026 this year. And Massimo will be visiting to present our paper. So welcome everyone, and we will go explaining what we did and what was exciting. So to first understand what was the motivation for the paper, we all know that LLMs are very powerful. They are large, they're tackling different problems in different areas, and there's so much we can do with LLMs, but there are fundamentally certain problems that in many cases they can happen. And one of the main problems that we have is it can generate harmful content, it can generate biased responses, and it can generate responses that are really not helpful, especially when it comes to mid-ranged LLMs, low parameter LLMs, or maybe even LLMs that are closed source, but they're not tuned properly in the way that we want. So has been a really recent problem, and there are the researchers have been trying to understand and tackle this problem in many different ways. The gold standard way of fixing this is to align the LLM. And for aligning LLMs, the traditional method is to do training time alignment. And by training time alignment, what we mean is that we fine-tune the LLM with the dataset data or reference data. This works really well. It is very effective in terms of most dataset benchmarks and real-life scenarios. But the caveat is that it's computationally expensive, and it requires full fine-tuning of the LLM. And it's not always feasible because let's say if we want something very quick, or we have a data set that we want to align this LLM to, it's not feasible because we need to do the training. Also, even for 7 billion parameter models, we need very high GPUs, like 4 and 8 GPUs, which is in many cases not possible. Researchers have been exploring the test time alignment method for aligning, which is a different way of treating the alignment. In this case, we don't have the training, so we don't have necessarily the problems of resources or time consuming. Everything happens at inference time. So at inference, the LLMs are tweaked so that it generates a better response. And often it's comparable to the training time. If we go back to the related works, in this case, we have the famous PPO algorithm and in reinforcement learning with human feedback. These are gold approaches to fine-tune an LLM. We have improvements on these methods like DPO, and we have CPO. So the fundamental thing about training time LLM is that the inference and the training, they are different. So there has to be a training happening for the LLM every time we need change in the LLM's behavior. Whereas in test time alignment, the scenario is a bit different. So there has been recent works like FTTT plan to align. So these models basically leverage an external reward model and use the signal of the reward model to adjust the generation of the LLM during inference time. So no training is required. And some notable works are C and Recontrol and RAHF. So these are based on activation steering or representation editing. So there might be different ways to do the intervention, but from a high level, what it means is that during the generation of the LLM, there needs to be some kind of mechanism that we augment the probability distribution so that the response is different, and the response that we want, basically. And of course, there's no training, and it works in many cases comparable to the training time alignments. In order to understand the baseline, so our work is mainly compared with recontrol, which is one of the interesting approaches in this activation steering mechanism. So the idea of recontrol is that it trains a value function to augment the hidden state of the LLM during inference to change the outcome of the generation. So to understand how the inference works, let's go through step by step. So if we have a prompt, for example, how do I hack a bank account? This is a harmful prompt, and we don't want the LLM to generate a bad response. We want the LLM to generate a response that should not say how to hack a bank account. So assume that we have an LLM, and we all know that we can get the hidden states from an LLM. And in this case, the hidden states marked in red. So if we don't have this value function, in an ideal scenario, it may produce a response that is not good. But the idea of this approach is that we want to augment this hidden state in a way so that the hidden state changes, and the generation should also move towards in a way that the response is better. So the authors do it in a way which is the value function, which is a very small 3-layer neural network, and that is responsible for scoring the hidden state. And when we have the hidden state scores, they perform a gradient ascent to augment the hidden state, to push the hidden state just a little bit so that it goes to the direction where the hidden state may not produce the harmful content. And when we have the new hidden states, we have a response that is good. In this case, it is illegal and unethical, which might be different if we didn't have this mechanism. So this is the entire inference pipeline, where the only dependency is that value function. So which we want to understand how the value function was trained. So the value function was trained separately before the inference. And the way it is being done is leveraging an external reward model. So for example, if we have multiple responses for the same prompt, for example, in this case, we have 2 negative responses and 1 positive response. And we have a reward model called Ultra RM 13 billion. This can be any reward model, but this is the one that the authors used. The reward model can score these responses with a reward score. In this case, you can see that it's my negative for the bad ones, and the good one has a positive one. So it's not always positive or negative. It's more like the better ones have a higher score than the negative ones. So these scores are then being simply used to learn a regression loss. In this case, the value function accepts the hidden state as the input, which is H, and we have the reward from the reward model. And this is being trained with the Bellman style target, and just this loss. And since the value function is a very small neural network, it trains very fast. And once the training is done, we can use it to do inference without any of this mechanism. So this is a one-time thing. The idea is to have approximation of the reward model with the value function that is responsible for scoring the hidden states. That's the overall architecture of our baseline. However, there are fundamentally 2 main problems or lackings in this architecture. Is that it trains on individual scalar rewards. If you look back to the responses, the reward model does not have any context on which one is the preferred one or which one is the non-preferred one. What it all only knows that I can score these responses based on some criteria that it was being pre-trained on. So a reward score of 6 or maybe plus 2.3 doesn't necessarily mean that it's a good non-harmful content. And in many cases, if there are examples in a sentence that there are multiple words that are positive, it can produce a better reward score even than the sentence itself is not a good one. And the second thing is that it ignores the pairwise comparison structure of the alignment dataset. So this model was trained with SHP and HHRLHF, and many other alignment datasets, which are basically main preference datasets. So for example, in a dataset, we have a preferred sentence and a non-preferred sentence. This is actually a criteria of the alignment datasets, which is not reflected in this architecture. And which actually made us question if the dataset is saying that we should pick preferred response A over B, then why don't we use this signal to train the value function and try and improve the generation of the LLM? So we tried to explore that particular area, and we propose Pref-CTRL, which adds 2 additional loss functions to the value model to leverage the preference signals and to make it understand that we should be generating more preferred sentences rather than the rejected ones, not necessarily based on just the reward model. So if we look at the very left, previously we only had the LLM generated text. Now we have preferred text and the rejected text. These are all coming from the dataset itself. Then we use the frozen LLM to extract the hidden states for these 3 types of text. In this case, the green one represents preferred hidden state, and the red one is the rejected one, and the purple is the LLM generated one. And we have the value function, and these 3 inputs goes to the value function, and the value function produces 3 scalar rewards instead of 1. And previously in the regression loss, if we go back here, the regression loss computes against with the R, which is the reward from the reward model. In this case, the reward model, the reward is marked as yellow. So we retain the regression loss, but we add the margin loss and a regularizer loss. So what are these losses? The margin loss is basically the log sigmoid of the preferred value function output and the rejected value function output. So href is the input hidden state, which is from the preferred text, and hreg is the hidden state for the rejected text. And the log sigmoid is basically saying that rank these 2 and understand the difference between 2 and make a distinction that we should be moving more towards the preferred sentence. And we add another term which is called regularizer, and this is computed between the actual generated text from the LLM and the preferred sentence. And this is because we want the value function to learn that the generation should be closer to the preferred one and do not deviate too much from the actual fluency of the generation. Because if we only use the margin loss alone, it could lead to reward hacking, and it may not always mean the generation is better. And this has two purposes we will explore right now. So what do these functions do? Basically, margin loss pushes the preferred uh, responses higher, so that it uh, it does not give more reward to the rejected ones. And the regularizer keeps the generation close to the preferred one, because if we push preferred too much from the rejected one, chances are that the generation might suffer. So this could lead to over optimization. So in theory, the value function may produce higher scores, but the generation is not really good. So the regularizer stops the value function from pushing the generated text too far. And this addresses the reward hacking in our experiments. And of course, the margin loss is very similar to the DPO loss, which is also another intuition for our experiments. Then we move on to the experimental setup. We explore two models here, which is Vicuña 7 billion and Hermes 3 Llama 8 billion. So Hermes 3 Llama 8 billion is an improvement from the actual Llama model, and it performs well in many instruction-based benchmark in this category. We use 4 data sets. So Stanford SHP and Anthropic HHRLHF. These are two known data sets in alignment, particularly in the harmful content alignment area. And we use these two data sets to train the value model, which we refer to by in-domain. And we use two other data sets, which is PKU Safe RLHF and Nectar. These are also in the same category, but we test our model in these data sets. We do not train the value model on this data set to check the performance of our out-of-domain scores. If our model performs better on these data sets without training on them. For evaluation, we use 4 different metrics. Win rate, that can also be referred as LLM as a judge. We use 3 different models for the win rate: Llama 70 billion, DeepSeek 70 billion, and GPT 5.1. And using different models from different categories actually showed us that we can check if the models are consistent in terms of using LLM as the win rate calculation, and not actually biased towards one judge. And we found in our experiments that the results generalize between all of these LLM as judge models. And then we have average reward, which is the reward model that we use for training the value function. So the reason for this metric is to understand if the value model can generalize when training with the preference signals and with the regression loss. So as we mentioned before, that the idea is that we want the value function to mimic the behavior of the reward model in some way. So the output from the LLM should reflect better reward score from the model. And we also calculate diversity and coherence, which is to measure the fluency of the generated content. Make sure that the generation does not lose its context. Then we move on to the baseline. So of course, we have recontrol as our primary test time alignment method for comparison. We also compare with DPO with LoRa fine-tuning. This is only for reference to the training time method. Of course, we mainly compare with the test time methods, but we also wanted to see how it compares with the training time method fine-tuned with LoRa. And we also check with 2 other baselines, which is best of n sampling, which is one of the primary works in this area. in terms of test time decoding alignment. And we also compare with CAST, which is also a recent one, based on activation steering, very similar concept to representation editing. We move on to the main results. So for our experiments, we conducted multiple experiments. So ideally, 2 data sets and 2 models. And we experiment with each of our components separately. So pref control with the margin loss only. We have the regularizer only. And of course, we have the combination of both. If we look at these scores clearly, we can clearly understand that our approach outperforms recontrol consistently in most of the metrics. Average reward and win rate across all judges in most cases. The combination of margin and regularizer performs better than the recontrol. If we look at the VQNR results on SHP dataset, we can see that our approach actually performs significantly better than the recontrol baseline. And in terms of DPO as being a training time alignment, but still we are getting comparable results to a training time alignment. Being a test time alignment, this is a very good indication that our model actually generalizes well. Then we wanted to explore the individual contribution of the loss functions. So if you can see that using only the margin or regularizer did not yield to better results. And this is because the 2 loss functions are very different, and it is necessary to use those loss functions in combination, because the margin loss actually tries to separate the 2 responses, and that actually makes the reward hacking more prominent. And whereas we cannot use the regularizer alone, because this is more the objective of the loss is mainly to reduce the over optimization of the margin loss. So this confirms that we need both loss functions in order to get a necessary stable signal of the preference and non-preferred sentences. The HHRL-HF is comparatively an easier dataset than the SHP one, but from the scores we can also see that still we get decent margins from our baselines and compared to DPO also, which confirms that our model actually generalizes in different models, even they are easier in most cases to solve by different approaches. Then the average reward metric, as we mentioned before, that we calculate this with the reward model that was being used to train the value function. In all cases, our approach actually outperforms all of the baselines, which indicates that the value function, even with the new 2 losses, has the generalizability to new data sets without impacting the actual scoring mechanism. We also conduct experiment with other baselines, as we mentioned before, best of n and CAST, and pref control outperforms best of n in every metric here. And CAST being a different type of method, which is activation steering, still our model compares competitively with it. So it actually shows that in test time scenario, this approach of using 2 losses and leveraging preference data is actually a good way to move forward. And we also experimented on checking the zero shot transfer capability of the model. So in this case, our model was trained on SHP and HHRLHF, but we tested on the PKU safe dataset and also Nectar. And we can see that in all of the cases, we are doing much better than recontrol, which is also an indication that we can use this use our approach in a new data set without training them necessarily. But of course, if we train train our approach on the new data, the value function, the scores would increase significantly. We wanted to explore also the effect of the hyperparameters. So remember that we leverage the gradient ascent to augment the hidden states. So there are fundamentally two hyperparameters here. One is the learning rate, and the other one is the number of steps to augment the hidden state. So in our experiment, when the learning rate is 0.5 and the number of steps was 100, we got the most higher results here. Another important thing to note here is that the peak here that we got is relatively stable, so it does not decrease suddenly, which actually suggests that the hyperparameter do not drastically affect the performance, whereas the preference loss is actually the main reason for the consistent gains. And here are some qualitative examples from the model. So in most cases, you can see that our approach handles the context well than the baseline. So it's not always about reducing the harmful factors. It's also about how to reframe the response and still not being harmful. For example, in this case, someone tries to get into the movie theater, but our model actually responds in a way so that he doesn't feel offended, but still not guiding towards the harmful approach here. And also this can be reflected in many other examples here. So in this case, to get results which understand the context better is actually another gain and interesting factor of our approach. With that, we are closing, moving closer to our presentation, and we have our implementation of the paper publicly available in our UTS nlPUG group, GitHub. So please check, and we will have the first version of our paper available when it's published. Thank you, everyone.
Thank you, excellent.
Should we move on to the QA or stop the recording first?
You want to record the QA or should we?
Yeah, it's fine. I'll go. Yeah.
I was curious about CAST. If you could tell us a bit more about what you mean by the intervention, if you had a chance to read it.
Yeah, so CAST is mainly a pure activation steering method, which is not operating on the hidden states. So in recontrol or in our approach, we wanted to augment the hidden state, train a value function. But in CAST, it doesn't do that. It mainly works how best of n works. So it deals with the probability and try to steer the output towards a better generation. So it doesn't necessarily requires a value function. It's a bit separate architecture, but yeah, it's a new framework.
But so it doesn't access the hidden state, but access the logic or the probabilities for the tokens.
Yeah, Exactly. Yeah.
Excellent. If we have any other questions of general interest, we can ask. Otherwise, we can stop the recording.
Maybe.
Oh, okay. Jacob, I can hear you. Yes.
Oh, sorry. Mine's maybe a bit more of a general question around the evaluation metrics. So like win rates. I mean, I've been out of the game for a while, so I don't necessarily know how that's the win rates are calculated, but like I assume if it's an evaluation metric, I guess that's used across like a broad range of tasks. How is the evaluation metric set up? I guess is my first question.
Yeah, sure.
Yeah.
The win rate and LLM as a judge has been very popular in many recent papers in terms of evaluating the answers from an LLM. So what it basically do is there's a structured prompt which is instructed with two responses. So for example, DeepSeek, there's a prompt for DeepSeek with the two responses. One is the actual prompt, and the other one is the answer from the model which is being tested. And the LLM as a judge is required to score these responses between 1 to 10, or maybe it could be a binary score. So if the score for the preferred one and the generated one differs by a margin, then it is counted as a win. If it's not, then it is counted as a lose.
Okay. So I guess then a follow-up would be like by the sounds of it, there's like a structured prompt so that every time you ask the LLM to judge the quality of two responses, it more or less gives the same answer. Is that true that like if you kept asking the LLM the same question with the same answers, it will score it the same every single time? Like, is it reproducible?
Yeah, it's a very good question, and this is something that we wanted to check during our experiments. So yeah, we did run 3 or 5 times the same evaluation criteria with the LLM as a judge by setting the temperatures to greedy, and the deviations are not that much, and it's almost always consistent with the scores if we are using the greedy approach to score them.
Okay, cool.
Yeah.
Thanks.
Yeah. Any other questions?
Yeah, quick one. So the reward function for the value function.
Yeah.
You said, I think is ultra RM.
Yes. Yeah.
Have you tried others? Do you think there's a strong sensitivity to the choice of the reward function for the value network?
So it depends on which data sets we are using, and which data sets the reward model was trained also, because in this case the SHP and HHRLHF, these are harmful content detection preferred and non-preferred data sets. So, and ultra RM was basically trained to detect and score harmful content and the generation. So it's more likely to be a good fit. But if we use something that is not trained with the harmful content, it would yield a different result, of course. So it is important that the reward model that we use is aligned with the data set, how the data set was prepared.
Yeah, and I guess the task.
Yes, yeah.
Excellent. Well,
small one.
Yeah.
Before, when I see loss function, there's a regress or loss
Yep.
and regression. Yes, I wonder what's on the next page, I guess. Yes, what's the difference between the L regression and L regular?
Yeah. Yeah. So
sorry, that's two different.
Sure. Yeah, sure. So the L regression is the loss between the generated one and with the ultra RM reward. So if you go back to this one, so the output from the value function, the hidden state, this is the generated output from the LLM, and we have the reward from the reward model. But we use the same loss as the regularizer, but with a different input here. So the input here is the value functions, the hidden state of the generated sentence and the hidden state of the preferred sentence instead of the reward.
Okay.
So we are training the value function to regress between the generated sentences score and the preferred sentences score instead of the actual target reward and the generated sentence.
Okay.
Is the usual issue with relative objective functions that if you don't have something to anchor it on a certain absolute value, we can make both go down, but like the relative was always tries to increase the margin between the two, but that can happen by making both very bad or both very good and just increase the margin a bit. So this helps to also put an absolute anchor somewhere in an absolute value, which in this case is implicitly the reward model that we use in case ultra.
Yeah,
the reward model and the score of the preferred of the two references.
Yes.
Excellent. Thank you very much. I believe we
you.
grilled you well enough. But keep it to this. Thank you very much again.
Thank you.
Fantastic. Thank you.
Thanks, Imran. That was good.